And share my screen. Good morning, by the way, everybody. So today we're going to work on mostly R. But before we go into that, what I want to do is, if you have questions about like Dolphin Next, you can always ask us. So when I look the runs, so I'm gonna show a couple of things. For example, this run. So we keep all the record history here. So for example, I'm gonna go one of these runs just to show you one more thing. So I see some of you guys have, get error, and to check what the error is. So we have these log files here about the errors. So we share the errors with you guys. Please come in. Why this is slow? Okay. So at the end of the log, usually we have like error, not this one, because this is terminated, I guess. Let me see, like one, for example, earlier run. Okay, so when you come here, so there is this work directory. Usually something happened here, for example, we don't know why now, but it tells you that in this work directory, we get an error. So what we do usually, we go to this directory. So you can copy and paste this directory in the cluster. Like I'm going to connect to the cluster first. In every run, it's you're going to see the same thing. So I just copy and paste here and went to that directory. So I'm there now. See, this is a working directory for that whole pipeline. And there are many more steps here. So you can see, for example, see, there are many numbers here. These are all covering one step in all pipeline. So you can actually go and see what happened in that specific step and what kind of code ran in that step. So you can look at this. But in this case, we got error here. And so, for example, this is like single cell pipeline, I guess. There are 3 files. It's doing something here. But just to see what happened here. So if you just use this ls-al command, you can see these hidden files, okay, in this directory or any directory actually. This is a cool command like ls-al. So, and if you want to see the error, the real error there, it's here, that command.error. So you can just look at it and see, for example, it's telling like, this is you know, there was a program here that owner wrote, I guess, and like some line, it get this error, and then he goes and fixes that error. So, or sometimes it will tell you that, you know, the file you try to use here is corrupted, or in that file you are using file number 180, there is this read problem, or those kind of things that you can read it here to fix the problem. If it's a corruption, for example, you can copy the files back. Or I don't know, like, you know, just if there's something telling you that, you know, it happened because of a reason that you cannot solve, that you can tell us that we can solve. Sometimes what's happening in our cluster, some nodes are not working properly. And we report those nodes, like which nodes we use, for example, to our HPCC admins. For example, I can show you these examples, zombie jobs here, see? For example, this node had a problem. So we reported this node, they removed that node from cluster that, you know, I resume my run here. I can come here. So there is this resume functionality. This is not my run, that's why I cannot resume, but when you click here, you're gonna see resume option, and you can resume that run to continue with, and it will take a new node and it will work that time. So that can happen. Sometimes If it is not working properly, just try to resume one time. If you still get the same error, and if you cannot solve it, just send us an email. We're gonna tell you the problem. Okay, this kind of things are happening all the time to us, but eventually, you know, you're gonna get used to it and solve many problems yourself. Okay, so any questions about it, like, you know, about this tool? Any feedback you want to tell us, you can tell us, or we have the support here. If you cannot send us email, this is also email. So when you write anything here and send that email to us, it comes to us and we answer your email. So you can use this support button here too. And yeah, any questions, please? Okay. There are no questions. I'm gonna go to today's session of my bootcamp here. Okay, so today we're gonna work on R&R Studio. I hope you install this. It's good to have RStudio or R in your computer, and it's gonna be faster. The things are gonna be faster in your computer if you run this. I can show you the difference. But what we're gonna do today, I wanna show you a couple of capabilities of R&R Studio, that we have many versions of R in the cluster. So I'm gonna just show like module available. And there are many ways to use R. And if you are running something like single cell RNA-seq analysis, for example, in R, sometimes I use cluster because my laptop sometimes busy or is not that powerful, or I need to use like stronger computers, then sometimes I use cluster. So I'll show you how you're going to use this in the cluster. There are two ways of using this in the cluster. One way is like, I'm going to show the versions that you can use. So they regularly update the versions here, R versions in the cluster. So where are they? Here. So for example, they have R411, the old versions too. So you see all these R versions, 3.6, whatever. So all the R versions here. So whatever you want to use, for example, if you want to use this R411, you're just going to load it. This is one way. You're just going to load it, module, load R411. And then when you run R, you need to use just R command like this. And now you're in R. So you can start using R here. This is all from command line. You know, this is the prompt. It's a different prompt you have now here in R. And you can do all kind of computations and stuff here, and then run some of the R scripts here. Okay, this is one way. The second way is, I like this a lot. We have this server, like web server, umassrc.org/444. Okay, so if you go here, it's going to ask your username and password, cluster username and cluster password, because this is on the cluster. Okay, this is another like web interface. It's called like GHPCC Open on Demand. So it's very powerful. So what you can do here is you can create an interactive application here. It's called, like, for example, if you want to work on Jupyter notebooks, you can do that. Or if you want to work on RStudio, you can do that too. See, RStudio server. So the good thing here is, actually, I did this one time, that you can create your own custom images and install the software into those containers that I was talking about last week. So last session, you can create your own images and install all kinds of applications there, keep it there, and then you can start that image. Everything will be installed in that image, and then you can still use RStudio server or Jupyter Notebook. So these are very powerful things, because the good thing here is when you launch, you're just going to press here to launch it. You're going to choose which version of R you want to use. And this is going to be interactive queue. It's going to be killed, I don't know, like in for hours. You write like how much memory you want, how many hours you're going to use. So then when you launch it, it's going to launch it, and you will have a session here in your interactive sessions. See, when I do B jobs, actually, I'm going to exit here. Oops. And when I do B jobs here, I have that running interactive node, and my RStudio is working on this. See, job name is RStudio. So you're going to see something like this in the background. So when you click this button, you go to your RStudio, and RStudio will look like this. Like most likely it's going to be clean for you. But the good thing about this RStudio here, whatever you write here, load into your, even you kill that process, everything will stay there, and you can continue working later on the same thing. For example, we are going to use this RStudio interface today here, or your own RStudio. This is the installation, for example, that I installed into my computer, and you can either use that or this version. It's up to you.
Alper, I have a question.
But I want to use this version just to show you a couple of things, because they're exactly the same, but one is your own computer, okay? And it's limited with your computer capabilities like memory and CPU and stuff. So sometimes your computers are not enough. But here you have interactive nodes. You know, you can start using this, and you ask the memory and time. You can run this on the cluster, and when it is done, see, like for example, I'll show you something. When even I close this, I'm not losing anything, so I can go back and connect back to the same thing. Even after you kill that thing, I can reach the same screen. And now I'm going to tell you like what we have here. You can ask questions, by the way. This is a totally different environment. You can either use, again, from the command line here. But when you're using from command line, by the way, don't use on the head node, and get like one of the, I was using this Q login, but if you want to use it, just get a node like this, interactive node, and use it from there. So this R, and then I'm going to do things here or here. So let me explain like what we have in RStudio. Like what are these windows here? So there are like actually four. When I open a file, for example, you can create a file here. There are 4 sections here. If you do this, like file, new file, R. Usually I use like this. So there are 4 sections. So the first section is, this section is for the editor, like VI, but it's not VI. It's much simpler editor. You just write, you don't need to use all these tricks or some commands in VI. So basically you're just going to write here 1+1. You can try in your own RStudio. But here, when you write things on this section, so you need to execute them in R on this side. So this is your console. That like the same thing here is the same with this. Okay, this is your like terminal. You can think that this is your terminal on this side. It's not terminal actually, it's like R console, because there's terminal here too. That when you can do other installations and stuff on the terminal. See, this is my terminal. That you can still use your Linux here. That's pretty good. But today, if you want to do these computations or like some statistical analysis, plots and stuff, you're using this console. Okay, it's ready for you. But to be able to execute things here on the console side, so basically, for example, I want to do 1+1, 2. You can either write here, but if you want to be more organized, I usually do like this. I come here and I write, like, for example, like, you know, say something. I want to do something. Okay, just write it here with like this, and then you can save this into your space here. So where is your space here? See, for example, on this side, bottom here, you can see your files. This is my home directory. Okay. And see, this is my home. And you can put your files into here. You can open it, create a new directory here. See, there is this new folder button. You have upload button, you have delete button, rename, and you can copy files from from one place to another. I'll show you what this set as working directory. So when you're doing stuff, for example, if you want to open a file, you can open that file from these directories in the cluster. So these are all your cluster directories. Okay, so that's cool. For example, if you just click this, any file here, like this is my script, my R script, for example. See, I opened that script that I used before. So in this case, I want to do the second one. This one, I want to save this as like, for example, my second script, whatever, or my test R. And you can choose the directory you want to save. In this case, I'm going to save just here next to them. And now I saved. So every time I do something, it will turn to red here. It means that there is something you change in this file. You need to save if you want to keep that change. Okay, with Command S, for example, or file save. Okay, so if you want to run things in your editor down here, basically this is important here. Some people are missing this point, but you need to press Command Enter. Okay, Command Enter. Okay, like I'm gonna put it here. Press Command plus or Control Enter if you are using Windows. Command Enter. Okay, when you do that, it's gonna go here and then it will do the computation in your console. So there are a couple of things that you need to learn. We put this a couple of slides, but I want to go over those things myself now. It's gonna be faster because I was going extremely slow. But I want you to do this as homework later, like to do these things yourself. So where was it? Here. Okay. So we have like a video here and also like some basics of our programming, like workspace, sequencing, numbers, vectors, some subsetting of the vectors, but I'm going to go over that now. And then I will continue to create those plots today, hopefully. But when you have questions, please ask. So what I'm going to do now, first, I want to tell you what a variable is in R. So variable is if you want to put some numbers, strings, letters, whatever, into a variable, usually it's a good way of working in R because sometimes, for example, you just put these numbers in this and you do a lot of computation using these things. So once you change the values in these variables, you can go and run this and it will do the same thing. So for example, in this case, what I'm going to do, I put A into 2. Let me clean here first. So you can clean your environment and I'm going to tell you what this environment is that you will understand better. So there's this button here if you want to clear in the future to clear your environment. So environment is something that you can put your variables into the memory of that machine that you're using. Later, when you exit, it's putting into file and then reload them when you come back again, when you close the screen here or this page. So when I do this like A, I put 2 into A. See, this is my variable and the value in the variable is 2. Okay. So when I do this B3, it put that into my memory here. So into my environment. So, but every time when I do this, I didn't forget like pressing Command Enter button. Okay. So when I do this, for example, C, like this symbol, you're going to use like this bigger than and dash just to assign this computation. You know, I just sum A and B here to C. Okay. When I do this, my C is 5 now. Okay. So I can do this many times, like, you know, it's going to be 5. But if you want to change the number here, for example, I want to change to 6. Even I change it here, if I run this, it's not going to change this because you have to press this Command Enter to be able to change the value in B, and then I have to do this again to do the computation here. See, everything I do is going to go here, and then you know, it will work all these things like this. Okay, so these are the variables. You're going to see, like, we are going to run these kind of things a lot. So today we will do lots of computation, like we're going to install libraries, we're going to use some functions in those libraries, and then finally you're going to start doing your differential expression analysis yourself here using RStudio. But to be able to do those things, this is the hardest part of R, I think, to do the installations. You know, you get lots of errors in the future. You're going to see there are dependencies. There are, you know, one library is using like 200 dependencies. For example, we wrote the e-browser, and it's using almost 200 other libraries that they have to be installed in the system. But you're using one thing to do the installation. It's here, like, for example, install packages swirl. So to be able to use this learning material here, you have to install this. Let's do that. I'm just going to show you here in my RStudio. See, it will try to install all the necessary packages. In this case, so where it is installing, see, it's installed now, it's done. Now I can use swirl. Before I couldn't use the swirl because it wasn't installed into my system. But I just want to let you know where they are going in your system, where they are installed. They are going to your local directories, okay? So there is this, in your local directories, you're going to see R directory and all these things. For example, I have been using R in many years. That's why I have many versions here, like 3.6, 4, and 4.1. In this case, some of them are still using 4.0, but these things are installed here. See, it's swirl is here. So if you want to remove all these installations and do the installations from scratch, you can always remove this R directory, and you're going to lose like all the installations you did before. Okay, so, but these are in your local directories and they take space. Sometimes you just want to remove those things to open up space. Just make sure, see, it takes like 243 megabytes. It's not that big, but still, there I haven't installed many things here. So after you install, to be able to use the packages here, for example, swirl is working like this. Swirl, it's a function, and you have to use this parenthesis after that to be able to use swirl. Oh, sorry, I forgot one more important thing. So you have to load any library. So whatever you install, you just install into your system. To be able to use these things in R, you need to load that, like library swirl, like this. And then this will tell you what you need to do to use. For example, type swirl when you are ready to begin. So you can do this. And it's going to ask you, what shall I call you? Helper, and then enter. And it's going to ask like what you want to do, which it's telling you like how to use this tutorial program. So swirl is a tutorial that will teach you some R. For example, if you choose one, it's going to show you how to do some R programming. Like if I choose one, R programming, and see here, basic building blocks, vectors, matrices, some commands, like all these things. It's just going to teach you these. It's good to do this, you know, like if you can start, and you have like 0%. I haven't completed this tutorial yet. And it will tell you what you need to do to follow. See, I just press enter, and then 3% is completed. And then I will do like help start, and 5%. It's telling you what you need to do here. For example, it's telling me now its simplest form R can be used as an interactive calculator type 5 plus 7 that I did here, for example, 5 plus 7. Okay, so, but I'm not going to do this now. Hopefully, maybe I need to exit 5 plus 7. It doesn't allow me to exit. Okay. Clear. No, it's not working, but that's fine. Not everything is working like in the console. So, but basically, this is a program like that. But if you want to get a help of something, for example, if I do this help, like, or swirl, like if you use question mark here, it will tell you how to use that specific thing on this side. See, I was seeing my files, but there are other things here that you can see, like your plots, the installed packages. Swirl is one of them. It's in this list, and your help will be here, and a viewer, that other files that you can leave here. So, but all the functionality of this library is here, and how you're going to use some examples here. So any command, if you want to learn how you're going to use, for example, there's a command C we're going to use now. C, for example, how you are using that C command. Examples here, for example, C179. So I'm going to do these kind of examples now. So let's start doing that. But some commands are already loaded into your system. Some commands are not. Like, for example, if you want to do D analysis, by the way, am I getting some questions here? You can stop and ask questions. Oh, there are lots of questions coming here. I don't read those things, but Arthur, could you like answer all these questions here? If you need me, just stop and ask, please. Stop me and ask, because I'm just talking now. I like when it is more interactive, you know, when you ask and I can go to those directions.
Alper, can you hear?
Okay, so what I'm going to do now, I will create another variable here, and what I will do, I will put like a couple of things into variable, and this is going to be a vector, like a couple of numbers, for example. We always use these kind of things. Like, for example, I will put 1, 3, and 5. Okay, this C is a function now here. This C here on this side, on the left side, was a variable. But in this case, this C is a function. Okay, you can use this as a function if it is inside of parentheses like this. Okay, so, and what I'm going to do is the resulting, first let me run this and you're going to see what's happening here. Oh my God, I need to finish this. Sorry, guys. I don't know how I can maybe stop the work. It was telling most likely how I can stop this, but help start, help stop. Let's do this. Help stop. So you can learn how to run these things. There is no help stop. See, they didn't write like how they should write, because there is this help start, but there is no help stop. I don't know how to stop this. Let me finish this then maybe you can learn stuff from here too. So what I did was I put this X, 5 plus 7 to X. So it doesn't allow me to run other things. That's why I need to finish this. So it's saying that to view the contents of the X, just press X. I'm going to do that. And now store the results of X3 into a new variable called Y. I'm going to do that. X3. Now it's in Y, see here. And what's in Y? It's saying you're doing so well. And now it's telling this type C, whatever. See, the same thing I was going to do actually. So when you just run this, you just see what is it inside, okay? And then it's telling this, just put this into another variable Z, and I put it there. And now I'm just gonna, oops, for example, C function. Oops. This is going to show me how I'm using C function that I showed you already. And type Z. This is the content of the Z. And create a new vector, and that contains Z and 555 together. See, another thing you could do with this is you can use another vector, for example. You can put them into Z again, but you can put Z, comma, 555 with C, of course. Function is important. See, now when we do Z with Z, oh, sorry, just want me to do this. So it's just, you need to just follow what it wants. And then the next one is like, you have to do Z by 2 plus 100. Oops. And now other operators, like you can do what it does. This was a vector. When you multiply everything by 2 in this vector, and it just added 100 to all the things here. And now it wants me to do like get the square of X, or no, it's just telling what it is. And now take the square root of Z minus 1. So basically to do that, square root sqrt, you could do like this. This is the command, like it's telling here, and Z minus 1. Basically, you're just using the functions like that. And then it's telling me that put the results into this variable, my square. Just do that. And now it's asking me if, before we view the contents of this variable, what do you think it contains? So is this a single number, or the length is 0, nothing inside, or length 3? So if it was a single number, it was going to be something like this. But in this case, we know that it's like this, you know, you can see it here, you know, like number, 3 numbers in it. So in here, it should be number 3. Okay, so we finished 58%. So it's great tool, I think, to learn many things here. That's why you can follow the others yourself. But let's finish this, and I want to continue with other things. And now division, it wants me to create a new variable, and it wants me to divide all the Z here with this one. Divide my square. This. In this case, my div is like, see, these are the division of this divided by that, like Z divided by my square T. And you see the division, and it's like similar vector, like they have three numbers in it. And the answer is the first element of my div is equal to first element of Z divided by the first element by Z. This should be the answer. And go ahead and look at the content of my div. And now Z was a vector of length 3, but technically 2 and 100 are each vectors of length 1. Okay, let's go. It's just, you can do this. I'm just want to tell you other things. That's why I'm going fast. Okay, I'll try to add this. And what it did, for example, if the size of 2 vectors are not the same, if you want to add those values together, what it is doing is just adding this, the first 2, and as you can see, 0, 10, and last 2 again. So it's adding, by the way, something like this, 0, 10. Okay, these are like some stuff that might make your job easier sometimes. Okay, so it's adding this and that, but you just give it like this. Okay, so, and if you want to do this, see how R is going to handle. And what's going on? Arthur, are you calling me? Could you talk, please?
Alper, you don't hear us.
What's happening? I don't know. Is something going on? Sorry, guys, I don't understand. Something is going on. And I don't understand. Oh, I cannot hear you. Oh my God, sorry. Sorry, guys. Could you talk again, please?
How about now?
Okay, perfect. Sorry, guys.
Okay. I'm sorry, Alper. I couldn't find any way to startle you. I'm sorry.
Thank you. No, I was checking the chat, but okay, now the last one, because other people are writing.
Yeah.
Stuff. I was missing the chat. I was checking the chat. I couldn't realize it. Sorry, guys. Tell me the question. Okay. What was the question?
Well, I mean, you were not hearing us in general, so I just wanted to stop you for a sec.
Okay.
They asked questions. Yeah.
Is
They
there
asked questions before, but we answered them. No problem.
Okay, perfect. Sorry, guys. I was just moving, you know. Okay, so we're almost done here. And type info for more information. And okay, so what is that? Main. So I'm gonna just exit here. Okay, so this exit will work. A 0. Okay, finally, I exit. Okay, so good. So this is how you can actually do these kind of things. Yeah, exit, most likely 0, 0 would work, but I didn't remember that. But there are lots of tutorials there in Swirl, and you can do all of it later, and to learn some details and read whatever written there. And I know like many people like that thing. That's why I put it there. And for each one of them in the bootcamp, we put a video too, because sometimes you're stuck somewhere, you know, like the ones that I was thinking that these were the important ones. And when you're stuck somewhere, you're writing everything, it's not working. And maybe you can watch these video, go to that specific question and see what we wrote to pass, because you cannot pass everything sometimes, and it takes a lot of time. Okay, so let's go back and talk about like reading files and putting some strings into the variables. Let's start from there first. So here, for example, what I want to do now is I want to show you that how you can actually put some strings into some variables. Like, for example, I just want to put A, B, and C. See, I use the same function, but only I put letters this time into the same variable C. See, my C changed. Now it's a character vector, not number anymore. It was number before, and now ABC in it. So you can add these kind of things. You can put them together too if you need, like numbers and characters together, but the overall variable will be character. So if you look at the summary of that thing, of that variable, you can query what they are. Okay, so for example, I'm going to create another one, D, C, for example, XYZ, X, YZ. We do these kind of things a lot. For example, if you want to define the conditions for your samples, and you write like sample names into one and the conditions in the second one, and you'll prepare your data set to be able to run DSeq algorithm, for example. That's why I'm showing you these things. And I do this and that, C and D. See, if I want to put them together into another variable E, you just use like C and D. So I know it might look complicated at the beginning, but you can see that this C here is always a function because I'm using them in the parentheses. The other things I'm using can be different. You know, you don't need to use always C or D. These are variables. You can give any name. You can give like C1, D1. Okay. And it's going to work. So E, my E is here. So A, B, C, X, Y, Z. See, and it's just merge, concatenate the vector, two vectors into one. And I have one vector here. Okay, this is cool. So now let's start like working on some files. What we do is like when you run, for example, Dolphin Next. Okay, so you're gonna have these kind of matrices here. Let me do, for example, my Amazon. You can, you already have these tables somewhere, but I can maybe show it where in the bootcamp session. But basically what you need to do, in the bootcamp session, you have these files, like you can download this file here, okay? This is in the URL. So basically what you're gonna do, we wget and download this file, okay? And let me do that into my desktop. If you are using desktop, do that there. Like in your computer, just go to your desktop, for example, like this. If you're using your computer, do like this. Oops. Sorry, curl. In this case, in Mac, there's curl function. Either you can do like this, or you can just click this. You know, you can click this and it will download it into your downloads folder. But if you are using these things on the cluster, just go and put it into your home. For example, I'm going to be on the cluster. I'll go to my cluster. So prepare that data because we're going to play with data today. And I'm just going to do this wget. Curl will work here too. I'm just going to get it here. See, I had already one version is there. That's why it created the second version. It didn't override it, but you can run it like this if you don't have it, if you haven't done it yet. So data is there. And what I want to show you, I want to show you a couple of examples that how we load the data there and start playing with the matrices and tables. But how you can actually get the data, it's not always going to be there. You know, it's not going to be like, this is just an example here. But if you want to work on your own data, you can have a run like this after RNA-seq run. You click here. Okay. So when you click in the report section, you're going to have this RSAM module as a table. There are other tables too, by the way, here. So if you want to plot the number of reads in a bar plot or something, you can download these files here too. There's download functionality, or you can go to the RSAM table here. See, this is a whole table. There are like 23,000 lines in your run. But if you use another like annotation, another genome, another organism, for example, this number can be different. So you can download this file. So, and then you can use that file in your R. Okay. So the other thing that is cool if you want to access those files from web. You know, all these files are web accessible. So for example, just to see where they are, I usually do like this. There's open web link in the logs of this. So if you just click here in the log, how I did was like this. See, in the timeline, there's open web link. So we create like a one hash here and put these files into the public directory. It's VPN, so it's not accessible from outside. So if you go here and then remove this last run timeline, I just want to show you what you have, like public files here, like for example, summary, some sequentials, all these files are here. So you can actually download them, copy link address and download them. Okay, these are the things that usually, for example, if we produce some BAM files, big files, we put them here and then load easily into our IGV by just using their URLs. That's why this is very handy for us. And sometimes what we do in the example that we're gonna do later is you can load things like this kind of tab separated files using their URLs using R2. So in the as you can see here in the report section, there's an example in our markdown here. Okay, so when you install all these like things, RCurl, for example, after you install this, and we're going to do that today. So when you install this, you can just enter this URL here and then read the file from that URL and then start working on that. So these are very handy for us because you don't want to copy files all the time and then start working on them. Sometimes you keep them here and then load from URL and then define your, like using the C, for example, I was showing the name of the columns here and select columns and start doing all these things. So today I'm gonna show you all these functions, hopefully, that you're gonna start creating them yourself. Okay, so any questions? Yeah, I was able to exit. Yeah, 0. I learned it at the end. I forgot that totally. Thank you. So yeah, you can exit with 0. 0 was for exit, not exit. You know, everybody is writing their code like themselves, and it's sometimes not intuitive. And the help stop didn't work, for example, if you want to stop, but you know, I didn't know that. Okay, so let's continue, and we download this data file. I hope you did too. You can either upload this button or you download it in the cluster. I did it on the cluster. And now I'm just gonna delete this and we'll start some real stuff, like reading the files. So there's good thing here, like called import data set. Okay, this will tell you how to read the files too. So in this case, I'm gonna just use this. And when I'm using this, it will run the commands here. And then we can copy and paste to keep on our records. So in this case, I'm gonna use my data.tsv file. It could be anything. Oops, what was that file? Let me choose it. Where was it? Data.tsv. Okay. Okay. I don't know. I wrote the same thing with the one, but okay. So here, what you're gonna do, the name of the data, you can change it here. In this case, we know that I can show you with head data TSV. So this is tab separated file. It could be comma separated too, or something else. So, but we know in this case, this is tab separated. And you're gonna choose the separated tab. It's default, but it could be anything else. So it's semicolon, comma, white space, whatever. So, and the heading. So the header, we have the header here, the gene transcript, whatever, all the things are here. You can select this yes, and you're gonna see why. And I will play with that command a little bit. And there is also yeah, let's load like this first, and I'll show you more. So now my data is loaded. Okay, so it's here, like the header is like looking like header here. So there are two commands actually it used. One of them was this, so I just copied from here, because when you run an import data set, it's just basically running some functions. And the second one was this VO data. You could have write this by hand too. If the location of the file is different, you can write them here too. If it's in another path. For example, if this is in your project space, project UMW, your PI's name and stuff, you can write them here. But in this case, it's on my home directory /data.tsv. So if I set my home directory as my working directory, set as working directory, for example, and it's using this command, set working directory WD. So then I don't need to use this tilde anymore here. If I do put this to the beginning, for example, when I'm running first one, this second one, see, this will work data like this. Okay. And then when you press this, it will view into another screen like this when I run this. Okay. So these are some cool functionalities. And let's go back. So this is how you load the file. But today, what I want to do is I want to show you another function. So read table. That was another function when you import it from there. You can change it, by the way. Oops, where is it? Here. So you can use this function. This was using the read delimiter function, but there's lots of read functions like read table, or if you want to read Excel files, there are other functions for that. You can search like, read CSV to delim, diff, Fortran. There are lots of read functions here that I'm using some of them. Say read table URL, for example, those kind of things, but those are replaceable. So usually when you use read table, it's doing like what read delimiter is doing. But I like this one because you can define your header, and also if you use this row names is equal 1. So for example, this is RSAM counts. I'm going to put, let me do like this first and show you one by one. So when I do like this, read that table, file means my file. I'm going to put this into a variable. Like either you can use this because I set the directory here. I can just do this. And when I read like this, RSAM, all RSAM table came. But in this case, see, there's like one difference here. Where it is coming from, it's header, because I didn't set the header. True. See, my headers are like V1, V2, V3, it's going like this. But here, header is in the first row, so I don't want it. That's why we have this flag, header true. Okay, when I do this, RSAM, there's this function too, by the way, head, like you have in Linux, in Bash. It's similar, but you are using different way. So in this case, you are using the functions in R, totally different than Linux. You're just using this head parenthesis like this. See, it's just putting like six rows in that table. Now you have them here, 6 rows. But what I want to do, usually we are using these tables like this. So we are putting the first column, these are the gene names, into the row numbers. And it's just, again, like makes this data structure easier to use. So you're going to see that how we are doing. It's like you just put this row names is equal 1. When you do this, See, now it's not 1, 2, 3, 4, 5 like this anymore. These are the gene names. Cool. So, but why I did that? So now this is not a vector anymore. So in the vector before, when we had, for example, like C, A, B, and C, this was my vector. And when I do like A, this like this brackets. So when I use like this A1, for example, this is going to write A. So the first element in this vector is going to be here. Okay, the first element, A. If I want to reach the second one, you can do like this, 2. Or if you want to reach out like from 2 to 3, you can do that, B, C. See, 2 to 3 just gave me those. So these are the indices of the elements in the vector. So now I can use similar things with a matrix or table in this case. So what I can do, for example, if I want to go the first element in the table, these brackets, okay, the first element is going to be 1. I want to get this gene, for example, and the third column, okay, you can do like that too. So in this case, this is the row number, this is the column number, but you need to use comma in between. This is important. So what you can do basically, if I run this, it's 0. Yeah, it is 0, I know. But let's do second one, for example, 47, just to show that I'm going to the right place. See, 47. I'm here now. Second row and third column. But if you want to print like multiple columns, you can do again like 3 or 4. But how I'm going to do this, how I can enter like 2 characters here, I cannot do like this. So I need to, it's always like row and columns, rows and columns. So if you want to put multiple columns here, you can do 2 things. One is like, you can put, for example, columns. I create a variable for this, and I put like 3 and 4. Okay. So, and I can put the columns here now. See how I use variables. I always put these things into these kind of variables. And the C3, 4 is going to be inside of columns. Let's do that. See, columns includes 3 and 4. And when I do this, see, 47 and 36. Column 3, 3, sorry, 2 and 3. Oh, sorry, 1, 2, 3 and 4, 47 and 36. And the column names are here. See, when I do like this, I can go to that gene and those numbers that if I want to get, for example, if I want to work on those numbers, so you can easily get those things like that. But the one more thing here that you could do was you don't need to put this into the variable like this if you're not going to use the same columns again later. You can just put like this too. So it's going to work. Same thing. Okay, when you do these kind of things a lot, you will understand all the logic. But you can follow. Any questions about this while following me today? It is the symbol for tab. Yeah. Okay. What does /t means? It's this is escape character. You know, you remember when we were talking last week, in the last session, we were using like in grep, for example, or awk actually, we use this /t. It's a tab character to put the separation while you're creating your tables. And then when you open, you need to use that tab T here. Same thing. These are in many languages the same, like in Perl, like the same, in R, it's the same. In many languages, we use like similar escape characters. In awk, it's the same. Okay. So now let's move on a little bit more about like how we can access using their names. So to be able to access some gene names, for example, if you want to see like genes of interest, like my genes, you can create such thing. And you can put the gene names here now, like I want to do like FGF21 and SP2, for example. You can put as many genes names as you want. But again, see, this is how you code. The strings has to be inside of quotes. All strings has to be like that, defined like that. The numbers are not going to be like that. All the strings, like, as you can see the difference here. When I'm using this my genes, now, instead of using this index there, like second, third, whatever, I can use this gene names now. But why it is working? Because when I put the row names into the rows that I showed you, like here, rather than the numbers, if I put them like this, I can use gene names here in the first part of this code, like RSAM. I can put this my genes, and only for these two genes. If I keep this empty here, oops, I didn't run this. Okay, see, I keep this empty here, it will bring me all columns. Okay, means like I didn't select any columns here. So if I want to get multiple columns, again, you can use this columns and add them there. But if you want to, for example, remove column 1, see, you can use -1. It means that this transcript column is removed. Usually we don't use this transcript column when we are doing things today. But if you need those transcript names for some reason, you can use them. So these are different isoforms for this gene that we have in this table. So this is cool. So we can actually go choose any columns now and any rows in this table, any subset of rows, that if you want to create, for example, a plot to show the variation of these genes, you can easily select them and get the values and plot them. So for example, if I plot them, there's this plot function. I'm just going to show how it is looking. It's just going to put those, hopefully, in the viewer. It's not working. It takes time on the cluster, I guess. Oh, here, I don't know. We're going to see. It's when it comes, it comes. Sometimes it takes time. It's kind of operations. Let's continue, and I'll see what's happening here. Maybe something else happening. Okay, so let's continue and work on the columns now. By the way, but before actually I start doing this, I want to go back and this is just an initial introduction, I think, for how you start using it. And I'll give 10 minutes break, but because this might take time for some of you guys if you haven't installed these things. But I want you to install especially these plots, Gplots and DESeq2. You don't need, or you can do these things too, but basically what you're going to do, you copy these lines and install into your environments. Okay, it can take some time for some people. So I'm just going to install like biocore manager first, and then later I'm going to copy and paste these two. It's going to be fast for me because I already installed them, but for you guys, it's going to install all the dependencies. Say no here if it's asking like, you know, update something. Don't update for now. And I'm not going to update. And then when I'm using, actually, I'm just going to use this DESeq2 like this. It's not installed. Let me see. See, this is the hardest part of R, because I installed this long time ago, but it couldn't find some stuff. Maybe it's asking me to update, but let's see. I'll try and see. Okay, now 10 minutes break, and because this might take time, and 10 minutes later, hopefully it's gonna be ready. And I will be here and asking, if you ask questions, I'll answer them.
Hi, can I ask you a question?
Please.
Hi, so I'm using our studio, but I don't know if it's like a different version or something. I'm a student for the UMass role, and I don't have the upload button like in the file on the right, like
Import,
bottom,
you don't have import button, you said?
like a upload. So the new folder, you know, the new folder, and I have a delete and rename and more, but I don't have.
You don't have this upload button here?
Yeah, I don't have that. Is that because I downloaded our studio based on?
Because you're using this desktop version. You're not using our studio server version. This is on the server. That's why you
Okay.
upload files to the server. But this
Yeah.
version, for example, I am using on my computer. There's no upload button here. See?
Oh, okay. Yeah.
So yeah, you can use either.
Okay.
But you don't need to upload anything to your computer to because this is your computer already, you know. And you can go, like, for example, in this case, if you want to go to your desktop, it should be here.
Yeah.
You
Okay.
can load some files.
Okay. Yep. Thank you.
You're welcome. Okay, so let's start. So one more thing, I told you that this is very hard. The hardest part of R is like installing the packages. Okay, you're gonna use these things a lot. For example, I was getting this S4 vector problem because there's a warning here. You know, they had problem. So it's always like this. You know, we are also maintaining a package in bioconductor. Means like, you know, people are writing the software and bioconductor is always upgrading to a new version. In this case, for example, this is 3.14. The release whole bioconductor release is 3.14. So what they are doing here in bioconductor or in like our repositories that other places. So basically, people are writing these codes and sharing with the people. Okay, and when they're sharing, you know, these people, the authors, are maintaining this code. But if it's not like installing everywhere, that, you know, these machines, like they are testing this on these machines on Windows, Linux, and Mac, and usually it should be okay. But when there's warnings, you know, it's just not working perfectly. So in my case, for example, I couldn't install it. So what you can do yourself. So there are two ways of installation in R. So if you're gonna work on R a lot, you need to solve this problem. Okay, you need to learn how to do your own installations in R yourself. Otherwise, it's gonna be really painful. Once you install, it should be okay in your laptop, but in the cluster, as you can see, they're changing stuff on the back end and it's not working for you anymore. So you need to learn how to solve these kind of problems. So one thing I'll tell you is this: while solving your problems in RStudio on the cluster like this, for example, I installed both of them. It took like all this 10 minutes actually was enough to install them. But when I was loading library, this gave me an error.
Alper, can you share?
Yeah. Thank you. I always forget that thing. So this took like 10 minutes. And so this thing gave me an error because this S4 vectors are not for like it. There was a problem that specific package that DC2 is using. So what you can do to solve these kind of problems is, so you can always install any package in here, or there's another command. So this, if you just write the session info, okay, so you can see which version of R you're using in the cluster. You can change this to, if you create your own image and stuff, you can change this to 4.1.1 or the new versions for 4 or whatever. But in this case, my session here is 4.04. Okay, so in the background means like, you know, in the terminal, you can either like do your installations here, or you can go back here and do your installations here. Okay, so in this case, for example, if you want to install the specific version, one of the old versions of this package as 4 vectors, or anything that you're going to actually do this a lot in the future if you are working on R. So what you can do is you can go to the bioconductor page of that specific software and then go and find like one of the versions. I'm going to go one of the older versions here. See, this is bioconductor and it's telling you how to install the software here. Okay, and you can see other versions here too in other, for example, in this case, what I was using was my R was 404. I loaded into my cluster. So one way of doing this, like you can go back to, for example, this version 4.0 and or maybe, let me see how I can find that easily. Otherwise, I have to do the search and stuff. Oops. Where was it? Oops. S vectors. So source archive. So if you go here, there are like the archive of SVEC. Like for example, if I go S13 or 14, let's do this again. Sorry. See, there are different versions here, but I want to go one of the earlier version. So I just changed this to 13. See, this is 13, but I want to go one earlier because I saw that this, the one that I'm using 40, it's on 3.12. So I want to get maybe this one. Let me see if it's going to work or not. But you can copy this link address, that anything you found like this. So you can get that with like wget. This is the location. And the good thing that we have it in here is rcmd install. So this is going to install any packages you have like this you find on the internet like this. So into my R. And yeah, this is going to be more complicated, I think, here. I don't know, maybe you don't have this problem because I have been using many different versions. But if you have this problem, I have another image to fix this, so I can send you that. I've already installed version that you can start the DSig to install. Just let me know, but I'm gonna continue here not to spend time for now, your time, okay? Because I need to install the earlier version and then install this to be able to test. But okay, I'll continue now. But you know, these are very hard problems to solve. So if you cannot solve, we are solving these kind of things regularly. Okay, so let me do this here. So what I'm going to do is, so I was loading this RSAM. Let me load the DSig2 here. So the browser that we created, it has DSig2, and I'm going to put DSig2 here, library. I already installed this to my computer. Most likely you're not going to have any problem in your computer on these kind of things. Cluster has more problematic sometimes, but it's solvable. Okay, so one more thing, another command that I want to show you is one of them is source. Okay, the source in the future, if you start writing your own functions, I'm going to show this. It's very useful command that you can use. See, you load your libraries, you just basically write these things in the editor there and save somewhere. And you can always use your functions there. So basically, you don't need to write them now today. You don't need to know how, but you can use the functions that we wrote for you to simplify your job today. Basically, what you're going to do is you're going to install these packages that is in the bootcamp that you can see, hopefully, in your own computer. These are not going to be a problem. Again, in the cluster, if there is, we're going to solve that. But so once you install these things, when you follow all these instructions here, we're going to use, for example, ggplot. And some of the functions that we use here are going to come from this file. Okay, like run DSig, for example. We are preparing files for DSig in this function. You will understand what's going on here if you learn all these commands and if you follow all these instructions in the tutorials, then you will understand better what's going on here in the code. But it looks complicated, but actually it's not. Basically, you're just like writing a couple of functions and changing your data and preparing for DSig analysis. That's all actually. But we simplified it with just one function. You just send your data, columns, conditions, and p-adjustability cutoff, and log2 full change cutoff, and expression cutoff. That will bring you or differentially expressed genes. That's just one function. But you can create your own tool in the future and learn from how we create it. Okay, so let's do it here. In this case, if you want to use those functions that you write and put somewhere on the internet or your own machine, you can always use this source command to load those functions coming from another file. Okay, this is, for example, there are many other functions that I wrote. They all came in and ready for me to use. They weren't there before in my environment, but now they're there. So, and in this case, I'm gonna show you how you can load the files using the URL. Okay, I put the file into the URL here. Okay, if you want to try yourself, I'm just going to put this URL into, but there are other URLs there as an example here, but I'm just going to put this into our bootcamp. You can load the file. I load from internet, hopefully. This is going to work. And what I'm going to do is basically, I'm just going to load my library, curl, rcurl, and plotly, DC2, my D browser. And then I'll start doing the URL. See, just put this URL here. And then the second one, this text connection, is of creating that connection from that URL. Basically, I'm using like two different functions here. One is get URL, the other is text connection. So you can use the functions on top of each other like that. And then when I run this, it is created that connection with that file on the internet. This is very cool because, again, like, you know, wherever you go, if you move this file on any computer, you can actually replicate these results because it's on the internet. And now this is the command that we used, rsem. And I'm going to look at it, head rsem. Yeah, see, this is this same file that I could load. And then, but this is that file, by the way. This is a different file. There are 3 columns here, 4 columns. Not the data that I was using there, but you can still use that. But the things that we are going to do are more or less the same. And what I'm going to do now, I'm going to choose, let me do this, by the way. I'm going to change this to something that I want to use. Because that one, don't use that one because one column is, sorry, I realize it, one column is missing there. So use the one in the bootcamp, this one. Let me fix this. Use please this one, because that one has missing one column, one sample. Okay, so where was it? Here. I'm just going to change my URL. See, if you want to do the same thing again, change it like this, load it again. You need to run everything again, like from the beginning. Okay, like I started URL, file, and rsem, and I'm going to check if it is the same file. Perfect. This is what I want because I have like 3 columns here, 3 columns there. In the old one, there are like 2 and 3. We could have done, but I just want to be in the same page. Okay, so the data, let's don't do this for now. So the columns that I want to work on is these columns, control and experiments. And when I do this, basically a transcript column will not be there in data. Okay, so what I'm going to do from rsem, from this table, I'm just going to choose the column, these columns, and I put the results into data. Let's see. See, beautiful. My transcript column is gone. It could be other columns there too, you know. If you want to remove them, just use the ones that you want to select. Now, what I want to do is this. Where was it? Okay. So I want to create, by the way, this plot. Okay. So this is scatter plot. But what I want to do, I have 3 controls and 3 treatment, like experiments, what I want to do is I just want to get the average of controls and average of treatments. Okay, so how I can do this is basically you can create, for example, for your experiments, you can create such thing like this. See your experiments. And for your controls, you can create something like this. For your controls, you can easily access those things. Two different variables. I put experiments in one side, controls in the other side. And then what I want to do is there is another command called cbind. Okay, cbind is another command that you can use to put different things together. But before that, what I want to do, I want to get the average of these guys and put somewhere, and average of these guys and then put somewhere. So there are a couple of ways to do that. One is like you can use roll means. Okay, so it's basically like this. Let me do one by one. So for example, mean experiments. You can do like this. Sorry, roll means. Roll means. This is the function. And what I'm going to do, I'm going to use data. But this time, I want to use experiment columns. See, same thing, like data for all rows, because this is empty here, nothing. And for all experiment columns, experiment samples. Okay. So when I do that, by the way, just I'm going to show you how this is looking first before I get the means. See, I'm going to just do the head. See, only 3. So I know that those 3 are there. So I'm going to get the average of these guys, all these 3 with row means. Or you could have done this too. Like, you could use row sum command. There is also row sums divided by 3. You could have done that too. See, this is another command. Row sums. See, row sums. You can use that too. There are like lots of parameters and stuff that you can use this row sums, but I'm going to use row means. It's easier. And now for each row, for each gene, I have one average value. So let me show head again for this guy, just to show that it worked. See, for example, the average of this tree is 45. Average of this tree should be 1.83, this is 0 already. So good. So I have the expression experiments means, and I want to do for the control. Data, and I'm going to use this now. See, now I'm going to do the same thing here. See, this time, let me show you the head of this guy. See, this was like the second row is between 99, 53, 66. The average is 72. It's very, very good command that you can get the means. Why we did? Because we need like average to be able to create that scatter plot. We don't want to. Okay. You could have done it like only experiment replica 1, control replica 1. We have that plot. I'll show you that you can compare all to all plots. Means like you can compare this versus this versus that, this versus this, all to all. We have that too. I'm going to show you. But to be able to plot this, now what I did, I get these experiment means and control means, but to put them together, I know that the order, as you can tell here, is the same. So make sure the orders are the same, by the way. And the size of these guys are the same. You can select this, you can look at the size of these variables here. See, mean count, large numeric, 30,739 elements, and it takes like this much memory in the memory. this much space using in the memory. So they have to be exactly the same, and the order has to be same, because sometimes what I see, some people are like, getting data from somewhere and another data from somewhere else, and the order of the genes are not the same, but they use cbind command to merge them together. It doesn't work like that because the order is not the same. You're gonna make a mistake when you do the scatter plot. So make sure you're doing everything right, and look every, when I'm doing these kind of things, I always look ahead. I always look at the order. If they're the same, then I can use cbind command. What will this do is basically this. So I'm just going to put this into my average all variable. And now let's look how it is going to look. See, beautiful. Now I get the averages. So now I can plot. So my plot command should work now here, since I'm using my computer. I'm just going to use the plot now. It's not going to be beautiful, but look how it is going to. So it's running now. What is going on in my plot function? Okay, it's so slow. Okay, so it's this plot. This is the scatter plot. Who can tell me what is wrong in this plot? Why it's not looking like this? Why do you think is that? Anybody can tell me?
You have outliers.
What's that?
You have outliers. You get some very high.
Yeah, there are some high, but this is the same data.
Yeah.
But how I can turn this data there? See, this is like same data, exactly the same data I'm using.
Transform it using a log transformation.
Exactly. So log is a beautiful function that you can use here to put these values up there. So how you can do it, look, for example, this is 800,000 reads here in this gene, 800,000. And most of the genes are in this area. And if you cannot see them like that, but when you get the log of this 800,000 log 10, for example, it will be 800, the log, no, sorry, the log of this guy will be, I don't know, 5. This is it's going to go down like this. So if you do log 10 or log 2, it's going to be different. But let's do log 10, for example, just to see what it is going to happen to the X and Y axis. So basically, you can use this log 10 function here and do it like that. And it's going to be like how we want. See, 6, there's 5, 4. So it's just the log 10 of that value, like 800, I don't know, a million, for example, is 6. So you can see this portion of the data better in this plot if you use everything in log scale. This is X and Y axis. When you just apply this function, it works. So, but I don't like this plot. Some people are using in their publications like this, but there's another package called Plotly. I usually use this. It's better, beautiful. And ggplot, for example, other one, like in this case, let's use the ggplot to create this kind of plot. So you can change the colors, you can add some transparency to the dots, and you can change the sizes. You can do those kind of things here too, but I don't know, they don't look good here to me. So let's do that here. So basically what you need to do to use ggplot, it's a totally different world, by the way, ggplot. It has its own layers here. So in the background, you can define all these lines and stuff, remove them, add them. You can change the colors in the background. You can play with this. But let's try. By the way, all these things here on this corners here, these are 0. 0 means if there's count 1, if that count is 1, you see log 10 or any log 1 is going to be 0. If it is less than 1, some values are here less than 1. They are not integer values in this case because we use RSAM. RSAM use a likelihood function. They should be integer. If they're counts, row counts, they should be integer values. Means that either you have 1, 2, 3 counts per gene. But in this case, because it's using a function, likelihood function creates like some and non-integer values too. That's why you see some stuff here, but these means all zero. You know, when we do differential expression analysis, we're going to discover, we're going to look at these genes and remove them from our D analysis, because in this case, we have 30,000 genes here, 30,000, but when you remove like the genes close to zero, you're going to have like half of it, 15,000 genes, and this will change all the p-value, p-adjusted value calculations. That's why you need to remove all these zero genes. But how are you going to decide? It's going to come in a second. So, but let's do this beautiful plot. So what we're going to do is basically we need to convert the data to the data frame, because ggplot is require these data frames. Okay, that's why we do that. And I give another name, g dot, and this was my average all. This is case sensitive, so I just change it. So g dot is exactly the same thing, by the way. You can look at like this head g dot, same thing, but in the background, it has other functionalities. This data frame has other functionalities. Like, for example, if you get the summary of this g dot, it can calculate the minimum values in this column, like mean expression column, and median, and the mean, third quartile, first quartile, and the maximum. So you can understand what's going on in your data. It's a cool thing that you can have. If there are like characters or strings in this data, you're gonna see that. For example, in RSAM, before I remove this guy, so I can just get my data frame. Let me do this. DF, I'm just gonna say data frame. RSAM, because there are some strings there. I want to show how it is looking. Summary, DF. See, transcript is different. This is different column here, and the length is this. The class is different character. Okay, so you can tell what they are if it's not numeric. For example, this is extremely useful command, because sometimes you get a table from someone. Okay, in that table there are NAs, like, or no, like characters or something different. Something is broken in that file, for example. Then what if even there is one character of string in that column, the whole column, it's not going to look like this. Okay, it cannot calculate the minimum, maximum, or median values if they're even single character. We usually check these files and tables, and if there's something wrong, you know, you can see them in using this function, summary function, and then find that line and then fix it or remove that line and then continue your work. Otherwise, you cannot do any of these plots if there is, like, you know, something wrong in that file. Okay, so ggplot again, like, has lots of layers, but I just want to come up, like, you know, if you just do this ggplot, it's going to put the first layer. Here's just empty page, ggplot, and then you have to add the layers using plus. It's like an equation kind of thing, but it's just adding one more layer on top of it. The first layer we're going to add is, I'm just going to do this with g dot, just show how it is going to look like. If you just do that, but sorry, I need to define my some of my columns here. If I just do this first one, so basically what I define my X and my Y columns. In this case, my X and Y is different. It's not treat and control. I changed it, but in your case, if you just follow everything there, it's going to be treat and control. In my case, so these names are coming from the name here. By the way, if you want to change the columns, let me show that too. If you want to change the columns, there is like call names function. Call names average all, so you can change the call names like this too. I want to make them like treatment. Yeah, I think this is going to be better. Treatment and control, and we can use exactly the same thing. So when I run this, Now my new column names, as you can see here, treat and control. Perfect. Now this will work, treat and control. But again, like this is a specific thing for this function. These are the parameters of the functions. And first, you need to give the data here. Data is equal to g dot. I prepared here. And the columns needs to be selected like that. There are other ways too, by the way. You can look at geom point like this. Question mark, geom point. There are many things you can do here. See, it's like ggplot2. We are going to use that. Points, how you can actually define the points, what kind of parameters you can use, about the data, some positions, lots of things you can do here, and many examples. So you can create and change the colors, other things. So, but I'm just going to use this for now, just to show how it is looking. I forgot to run this. Perfect. Now it will draw my dots. But again, it's gonna, I don't know why it's just, see the same thing, but looks better, So now I want to add another layer here, another layer to change. You can go to the second line, you can add the plus here and then go in the same line, but usually I don't want to pass this line. I pass sometimes, but not many times. So you can define these things in multiple lines like this. So, but I'm sorry, I was going to add the color and alpha and size first to this G point, and then I will add I will change the scale. Or let's change the scale first. It's going to look better. So I want to change plus scale X and Y. If you just want to change, for example, one X scale to log 10, you can just add that one. It's going to be here when it's doing, I'm going to put the second one too. So sometimes you do that, like, sometimes you need to change only one scale, this can be a need. That's why they do this separately. And in this case, you could have done only one column too there before you bind. You can even put this log 10 here, by the way, if you just want to do only one column before you do C bind. Okay, but I'm not going to do that. Or you can even like do log 10 here. If you do like this and then prepare your G dot with the log values, and you don't need the scaling here. But I like doing like this. That's why I want to show you these functionalities that you can actually apply. So I'm going to do both. And then I will change the alpha transparency of these plots. So I will add, and I will change the size of the dots here. And for example, color can be, I don't know, blue. You can do whatever. Let's try. And then I will change alpha. It's going to be like transparent, like you can say, I don't know, 1/10 or something. It's going to be, or 0.1. It's going to be pale, but you see, like, this is important. Sometimes you want to do like this because you want to see where all the data is accumulated. In this case, it's in the middle. So you have less points outside of the middle. So these are the count values of the reads. So in control versus treatment, most likely these are differentially expressed genes. These are like upregulated in the treatment. These are upregulated in the control, or this is downregulated in the treatment. So you can see. So today, after we do differential expression analysis, actually we're gonna draw those differentially expressed genes. We're going to plot them on top of this as a different layer. So this is cool. We can do many things. I usually use gray. I don't know. Color, you can use a whole bunch of colors on different layers that we're going to use today. Okay, so So now I'm going to do this thing too. This is important. Like filtering those zero count genes, that how we do that. So first, you can create a histogram of your counts, total counts coming from all those. You see, this is great. Usually, I use this as a background, and then I color my up and down regulated genes with red and blue, red and green, whatever color you want. Okay, so let's get this histogram just to decide which genes we are going to remove, or what should be the cutoff I should choose to remove zero counts. As you can see here, or let's create it first. So I'm going to use this row sums, and just to find the, let me show what I'm doing. So for each line, I want to get the sum of these values. If they're all zero like this, I want to remove them. Or if they are like, I choose a maximum cutoff by looking at distribution. And how I looked at distribution, basically, this is the histogram function is going to create this plot. And you can use the breaks. 100 means like this break point here. So you can increase or decrease that number just to change the resolution of this distribution. So like this means, for example, if you say the 100, it's going to divide this like many smaller pieces and calculate how many genes have this expression level. Like in this case, for example, around 300 genes are in this expression levels. Almost like in this case, this is log scale again. 1 means 10 reads. So you can tell that like 300 genes around like 10 reads. Or if you go up here, this is hundreds, like log 10, this value log 10, like this is 100, like log 10 of 100 is 2. So that's why you can say 4 is like 10,000 reads here in these genes. So 10,000 reads in 300 genes again. So around like, if like most of the genes around like have around like 1,000 reads, means like, because this is the top. So you see here like a bimodal distribution, like there are two distributions here. So one distribution tells you that these genes are close to 0. These are the ones that you want to remove. These genes that you want to keep. There will be some other like genes around here that might be close to 0, but you can just think that those are like false positive. You can still want to include them. You just need to use a cutoff. So, but how we can do that? That histogram might be different for different data sets. If you have larger data set, more samples, this will skew like on to the right side. Or if your data set is deeper, if you have more reads, it's gonna go to the right. If you have like less reads, it's not that deep, and then this is gonna go to close to 0. So you can see where your data is distributed by looking these plots. Let me do that histogram. So you can create a histogram with some D with the break. You can change the break just to see, like I'm going to do 1,000 for example, just to show you. This. Yeah, log 10, a breaks. I need to run this first to get the sum, and then histogram. See, when I do 1,000, most of them are here. Sorry, I forgot to do log 10 again. It should be log 10. Otherwise, you don't see anything. All the guys are around there. That's why, and especially when you make it 1,000 breaks. So, okay, so this is when you make this 1,000. See, you see like the resolution is like more like, here, but most of the data is like distributed here. You can use 1,000, but usually I like doing with 100 because it tells me, it gives me a better picture to decide this cutoff. when I look here, you can see that distribution. And when you go to the middle, it's around 1. And you can do that line 2 with AB line function here, just to show. I'm going to put this around here, 1. 1 means 10 reads. So that's good. You decide, okay, now I'm ready to do my differential expression analysis, and I can use that as my cutoff to remove these guys and then continue with the rest. Okay, so let's do this too, and then we're going to take a break after this, and then in the second session we're going to start doing the. So this all-to-all plots I love looking at, because this tells you everything about your data for all the samples you have. Basically, this function is coming from this functions.r. Okay, so it is just making so simple for you. So in the future, if you just load this source, you can use it on your own data to do this, because it will tell you a lot of things about your data. Means, for example, what this tell you. So these are scatter plots, the same thing like we created, but for all samples, all to all scatter plot. Here, for example, if you want to compare the controls, these are your controls. So their like correlations should be high. These are Spearman correlations. So their correlations are extremely high, 98, 97, 97. So extremely high here. It means that your replication is good. So when you do your QC, quality checks of your data, you check this plot. And if the correlation is low here, for example, 0.5, or if you see some cuts here, or means here, so these are again the same read counts, X and Y axis for control replica 3 versus 2, for example, for this plot. If you something wrong in this plot, it's not like reproducible, means if you don't get the same count, similar counts in both replicas, then there's something wrong in that, and then you might need to remove that sample. So here, in this case, these are very good, but you always see this kind of like variation a little bit. You see like larger variation when the counts are low, like smaller variation when the counts are high. This is normal to see like this, because it is when you do sequencing, if the expression level of a gene is low, because of sampling, you get less of those and the variation will be higher. If the expression level of a gene is high, like for example, in this case, there are like 1 million reads coming from one gene, that 1 million out of like, I don't know, 20 million reads, 1 million of them is coming from one gene. Imagine it's easy to sample that 1 million, and you get that more accurate values and more replicable counts close to 1 million. That's why it's more like when you go up here on this side, you can trust the data more than the ones that is down there because of sampling problem. Sampling is like randomly choosing the reads, the molecules in your sequencing tube. Here, when you compare control versus experiments, you see the larger band, like larger, like triangle kind. It should be like a triangle, by the way, but a larger means the variance is larger. It's showing that there are some differential expressed genes in between experiment replica 1 and control replica 1. But these are mouse, human, and these are mouse, and their genomes are exactly the same. That's why you see this beautiful shapes, means like very replicable. But when you look at the data coming from donors, maybe the correlations are lower. It's not going to be like maybe 96 if you compare like cancer versus, I don't know, healthy. These are going to be like everywhere. Means maybe they can be still correlated, but larger bands, larger triangles you're going to see. Okay, so that's why this is an important plot. Okay, let's continue in 10 minutes to start doing differential expression analysis. Hopefully, you're gonna start doing these things yourself too. We will have a couple of commands actually. It's not that difficult, but you'll be able to do them yourself. Okay, now I'm ready to answer a couple of questions. Yeah, it's different versions. You're gonna see lots of libraries, lots of versions, lots of trouble. That's why we are using Dolphin X and D browser to keep things simpler. Even like these kind of installations are hard for us. I told you, like, you know, that when I was giving that example of Rachel Green's paper, I couldn't even install those older versions of the software like happened today. It's always going to happen, these kind of things. That's why I never work like this, like how I'm showing here. I always use my own image. Means I know every single version, they're already installed. I know they're working and they're going to work forever. It's not going to affect you. That's why I suggest people to use always Singularity or Docker containers and images, not to lose time. Because there are two ways. One way is just installing like this, like I was trying to do, onto that your own local machine. But again, like you're going to have these kind of problems. But if you have, let me show you, like, just as an example, what I mean by image. So when you create the image, see server using custom images. Here, when you click here, you can use your own image here. And I created one and I put already the EC2 and everything there. So this is the recipe of that image. If you want to create yourself in the future, this is how you can use Singularity. So like the bioinformaticians today are always working like that. And this makes your life easier because all this thing is like a Linux that you are installing the Linux from the beginning to the end. And here at the end, you install, like, you know, some, but these are not going to be installed. These are examples. But what you can do, you can remove these in this file, remove these hashes to install all these tools and packages with Biocore Manager, for example, and then they're going to be there forever. You know, they're going to work because the versions, our version will be 4. And in the background, nothing will change. So all the versions of the packages Linux is using this here, they are defined. They're not going to change because the recipe is here. And this means that this machine, it can work forever. But that machine in the background that you're using in the cluster, the people are working and changing lots of stuff in the background. You don't even know. I didn't know that they changed something, that my S4 vectors are not working anymore. You know, they're doing something. They don't tell you. That's why if you want to have the full control, you need to learn these things. Otherwise, you're going to rely on other people. Okay, maybe 5 more minutes. I'll get a coffee and continue. Okay. Let's continue. After introduction of that recipes, the machine. Okay, so I'm going to go back to my bootcamp. Okay, now we are ready to create scatter plots, volcano plots, and start doing some clustering using our differential express genes. Okay, so how we're going to do is like this. So we need to use another variable to define our conditions. So, but while we are doing this, we have to make sure that our treatment and controls, these names matches with our sample names, samples. Otherwise, if you just put a different order, it's gonna, the program is gonna take this into account as there are different conditions. So let's run this. Create a smaller. Make this. It's not working. Is that? Okay. So I'm gonna create my condition. So what I'm doing here, basically, this is just a string vector. I have like 3 treatments. In this case, by the way, see, in my data, the first 3 columns are controls, last 3 columns are treatments. So I need to change the order. And see, what are those parentheses here? The first parenthesis for the C. Okay, they put them together. And the factor means the DE-seq requires a factor, like a data frame that we created up there. If the factor is another thing that is changing the data structure. And when you look at the, for example, summary of the conditions, it should be something like factor. Let me see. Yeah, there are 3 controlled, 3 treatments. So it's just changing that whole overall like data structure, because if you just do this, I don't know, summary, I'm not sure if it's going to work like that. But see, when I just do this without a factor, it's just giving me, it's a length, it's a vector, the length is 6, class is character, mode is character. So this is just that. But when you convert it to a factor, it knows like there are, you in this is a factor, you have 3 controls and 3 treatment. So because DE-seq2 requires this kind of a data structure, that's why we are changing our data to that. So how we're going to do now, we have this run DE-seq command. This is like almost covering almost everything for your purpose today. But if you want to see the details, by the way, what you can do, you can just go to that function and run these things yourself. I'm just going to go over what we are doing actually in this function. The DE-seq function is this. The first row here in this function. By the way, this is just how you write the functions. Like, you know, run DE-seq is the name of the function, and you just use this assignment operator, and then you have function. It tells you that this is going to be a function, and these are going to be your parameters. Okay, you can create your own functions like that too. And but in this case, like, you know, you need to use the parentheses here before and after the parameters, and then you need to write the function inside of these curly brackets. Okay, this is from here to here. It's going to be my function. So here in the first row of the function, what I'm doing, one more thing here is like, if you want to have a default value of something, this was that would helpful to identify required data structures for different functions. Actually, they are telling you, you know, when you look at the help, when you look at the question is like, you know, any tips to understand like what kind of data structure a function needs. So they are telling you with an example in there. So if you do just, for example, the command I'm going to use is this, DE to data set from matrix. Okay, this is the DE function that I'll use. So if you just come here and do this, so it's telling you what kind of things required here and some explanations. Count data will be non-integer, like see, non-negative integers. So in our case, RSAM produce some non-integer values. That's why it's not going to work if I just give directly to this function. What I'm doing here is the first thing I do is converting it to integer. So this is just doing that. It's getting all data, all columns, applying a function. This is the function. It's very complicated structure, but if you need to convert anything to integer, just use this line. Just change your data, the name of your matrix. That's all. You can use this line. But again, like apply, there's a tutorial there. You can, after that tutorial, you understand better what apply is doing. And then we convert the factor inside too, but I did outside. It's not going to change anything. But I just want you to know that important thing. That's why I was doing outside. And then I convert the data frame and then use cbind. I add like the all column names of the data to conditions. Basically, I do this. I prepare this. Look, maybe when you see. So these are preparation to run DESeq. It's telling you here, by the way, with the examples and stuff. It's telling you what you need to do. You need to read it. But I'm telling you how we are doing. So this was the conditions, the factor. I have it. And now I just only get the column names of data. Look, the column names were like these sample names. But then I create a data frame. And my column, sorry, my column names are like this. And my conditions are like this. And when I put them together with cbind, it's going to be like this, called data. See, I have the column names and the conditions. And the DESeq2 requires this kind of data structure to prepare to be able to feed it. So you can do that yourself too. But in this case, I'm just going to run all this thing. And the last thing that you can get the subset of the data by removing that non-express using that count 10, you can remove all 0 counts. So basically, subset function is doing that. You send your data in, and a parameter will be the sum of that data is larger than this cutoff. In this case, it default is 10, but you can change it in the function when you're using. If you just don't send this function, if you don't put this, it will take it 10. If you change this like 1, 2, 3, 4, 5, 6th, what's it called, like the parameter, if you change it to 20, it's going to remove the ones below 20. Means it will keep only these guys, okay, using subset command. So we use these kind of things a lot while preparing the data for the plots. But in your case, we just put these things and simplified, and basically you don't need any of these. You just need your conditions and your data and your columns, this one. That's all. So I'm just gonna copy and paste from here. And this is like another function. You can change the name to there if you want. But what I'm gonna do, by the way, if you want to play, I'm gonna tell you one more thing. If you want to play this specific function, you can copy this, okay, and put into your here. Okay, so there's this button here. You can just close and open. It can stay here in the bottom or top of your script. So what you can do, you can select this. If you change anything here, for example, I don't know, if you change anything, group 1, and if you want to test the functionality of this change, or if you want to add more things into this function, So you can rerun this, like select all this thing. Now when you rerun, see, just change my function here with that group 1 here. Don't do it now, but I'm telling you that you can add more stuff in it. And the function, even you loaded before, this will overwrite. This run that I did now will overwrite the function that I'm going to use on my environment. Okay, this function will exist in my environment that I can use, and I can do any changes in this function. So you can actually learn faster by like copying other people's functions and changing them and then use them. So, but I'm gonna just put it back because this will give an error if I use like that. And I put back, I'm just gonna delete this now. So now I'm ready to run. My data is here, columns are there, conditions I prepared. I just put 0.01. This is the default value. You can change the 0.05 if you want. Sometimes you do. This is log2 fold change 1 is fold change 2. It's gonna bring us like fold change over 2 and below 0.5. So below 0.5 will be downregulated. Over 2 will be like upregulated genes in this case. And non-express cutoff is 10 that we find this number out from. I see. Okay, it's not. Yeah. It's not columns, it's calls in my case. In your case, most likely if you follow there, it's going to be columns. But in this case, I define calls. And now it is working actually. And this is real data. There are like 30,000 lines. And it's removing all the cutoffs. That'll be like 50,000 lines, 15,000 lines, something will be removed. And you're going to get the results here, and I'll show how. So let's go back here. So now we are going to create this plot. It's going to be so easy because we have another function, overlay significant function here. Again, that function is here. You can go look at, learn more how we are doing stuff. And basically we send our data and send the results of the selected genes. It will color with red, for example. Okay, so how we are going to do it? So DE-RIS, if I just show you what I have in DE-RIS, if you just write it here, see, with dollar, you can see detected genes or selected genes. Those are two different data sets. One is like selected means it's eliminating all these things using these cutoffs and getting only significant different genes to overlay. Detected genes are going to bring all the genes after eliminating those zero count genes. You know, it means those are detected molecules or the detected genes in your bulk RNA. That's why we say detected. Selected is selected using these cutoffs. And now let's use those detected and selected genes to plot this. So how we're going to do, first, we need to prepare this G dot. How we prepare the G dot. Where was it? Did I prepare that G dot here? Yeah, I have it here. So G dot was the one that I plot here before. By the way, there are arrows here. You can go previous plots with these arrows that you created before. It's like it's keeping the history. The plot that I think takes time to plot this, right? But it's there. So G dot data was my average data that I want to use, and I want to overlay my significant genes on top of that. So what I'm going to do is basically run this function first. And this will just overlay the data, okay? Your data structure. It's going to use G dot, the whole data, and it will put this data on top of it. And I can show you how it is looking. Basically, this function is just doing this. So this was my data. It creates one more column because you need one more layer. And in that layer, we can separate some genes to all genes versus significant genes. So if I can tail this, I guess I put significant genes to the bottom of this list. See, significants are there. All genes are on top of here. So what is basically going to do? Is this a question to me? Or you guys can answer. So I'm going to do the same thing here, but in this case, I'm adding like the same thing here, but I'm going to use this data now I've prepared, and I will add the color with this legend column. So you can actually use legend column to change a color and decide the color here in another layer. So let's do this one by one. So I'm just going to copy these first here. By the way, I'm going to show this was like what we did before. Okay. First, we did this. Oops. Treat and control. First, we did this. Now, we added the color. This, I changed alpha to 610. You can do like, this is 110. This is like 0.6. So you can change the transparency level. And I increased the level to 3. So this was 1. So let's do this. I will add plus. And I want to change the color to red, like red for the significant. When the legend is significant, it will be red. When the legend all, it's going to be in the background gray. So you can just set it like this using scale color manual. If you add more, by the way, if you add more names into this here, for example, upregulated or downregulated, or some gene set that you want to look like, gene of interest, you can change the gene legends for those genes. How you're going to do? Basically, you're going to do the subset like I did, for example. This was my overlaid data. Okay, you can change the legend for example, overlaid. You can say for FGF21. I'm sorry, I'm doing wrong. For FGF21, I want to, for its legend, see, this is, I'm selecting FGF21 gene and its legend. Okay, you can change that to, for example, sorry, you can say the gene of interest. So my gene, I don't know. You can give a name like this to this legend. It will just change that name here. And when I'm adding, like I'm adding extra thing here because you have this in the tutorial, but see, all is going to be dark gray. Significant will be red, and you can add, I don't know, my gene will be, I don't know, green, something like that. I just want to see, like, this should be there, if I did it right. Okay. See, my gene is equal to green. It's beautiful. So you can do subset of the gene just to see where they are on your plot. And one more thing that I want to add, the scales. And then see, this is the whole command, by the way. What I do, I use this plus to merge this layer. And maybe let's put like this. Maybe it's going to be, this is another layer. This is the second layer. This is the third layer, third and fourth layer scales. I'm going to put this here. And then when I do this, Let me do, what is that? ggplot. What is wrong with that? I forgot something here. Let me copy it from here. Ah, okay. Let's do first this and then see what I forget. Okay. Oh, sorry. You have to run it from the end, not from the beginning, because when I do this, it's just running only this line. Oops. Okay. So what is different? I don't understand. I'm doing something wrong, but there's something wrong here. When I'm adding things, I forget something, a character or something somewhere. I don't know. So hopefully, yeah, my gene is somewhere here, but it's in the background. Let me change this to another name. Maybe it's going to the background. I don't know. Or it's because of the name or something. I don't remember, but should be there. Let me see. Maybe it has to be at the end of the, yeah, the problem. It's there, but somewhere in the background. It has to be in the, at the top, at the bottom of that whole thing. So I need to, like I did here. Yeah, that's why, you know, it's putting layer by layer. So I just changed this, but I need to order it and put it to the down to put this later. But how I can do that? I need to order this. I forgot. Whatever. It was, yeah, it's not gonna, but I sold this in the browser that I'll show you later. But whatever. I'll send you how you can put this down there easily, because it will take time if I just remove it there and then put to the bottom. I don't want to do it now. Okay, because I want to show these other plots. So we have two more plots. One is MA plot, and MA plot is basically just plot MA. I didn't write this function. This function is coming from DESeq2 in that package, and it's just basically creating MA plot. Some people like MA plot more, and they use this. And another one is volcano plot. I wrote this inside of that function. If you want to see how we are doing, again, you go here, volcano plot is here. Okay, so basically in volcano plot, what you're doing is this. So the results are coming from here, and using a cutoff, the color, and the fold log2 fold change. On your x-axis, you have the log2 fold change, and y-axis, you have minus log 10 p-values. Okay, so you can see which genes are up or down regulated, and it's another way of visualization of the same thing, but different x and y axis. Basically, these three plots are same, but different way. So in MA plot, what you do basically here, this is M, this is A, means like multiplication, and this should be like addition or something. But what you do basically, these values here in the scatter plot, it's coming. So you just multiply this guy with this guy in the MA plot, they're going somewhere here. And when you get the, when you divide, when you get the fold log2 fold change from this to this, they're gonna go to your y-axis. Basically, it's like this. That's why you see it. Like some of them are here because you do the multiplication, and it's just transforming data to another coordinates. That's all actually. So this is log2 fold change. This is mean of normalized counts, basically multiplication. That's why they call M. And the volcano plot was again the same thing, with another way. So log to fold change, same thing like MA plot, but then you're not using the exact values here, you're just using the p-values. It's a different value. So that calculated using DEC2 with this function that we run. And when you look at the results, actually, I want to show you that too, how it is looking. So you might need to use it in the future and use other things. There are some statistics and other stuff there that you might want to use. See, we have the results are coming like this for each gene. You have the mean of all the genes that we did, but not only for the experimental control, but everything, the mean. And the log two-fold change is calculated by DEC2. It's using another function and adding like some pseudo counts, because when you come down in the list, like for example, if you have 0 counts in one case, it's just adding a count there before dividing, and it estimates the log two-fold change for low counts too. It's working more or less, but these counts are you believe them more when the values are higher. And then it's using this p-value calculations, and another thing it's doing is calculating p-adjusted values, which means that it's just taking into account the number of tests DEC2 did while doing this operation. Means, for example, if you have 15,000 genes, you do the tests 15,000 times. And when you do 15,000 times, by chance, one of them, or like a couple of them, some of them can come, that the values can come this low by chance. So you need to multiply the number of tests you do. Basically, there are a couple of corrections like Benjamini, Hochberg, Bonferroni correction, like that. There are a couple of corrections like that. You can ask the details to Bruce. He knows everything about those, but there are papers like about it too, so you can read to learn how they are doing this correction. If you don't do this, you can some of these genes might look like significant, but actually they are not. It's just by chance the number looks low, because you are testing this similar thing again and again 10,000 times. By chance you get it, like that. The normal distribution, you're just trying to remove that by chance that you get on the one like 0.01 like 1% areas that you want to just decrease. So increase the p-values by adjusting the number of tests. So this is important. I always use p-adjust values. Usually we never use p-values. Okay, so I think we are done with the volcano plots, and now we are ready to look at post-processing QC. So means now we want to visualize this like up and down regulated genes or some genes, or we want to do this post-processing QC just to check how replicable my DE analysis results by clustering them. Like what we are expecting, that when you cluster them after DE, for example, you expect, or before DE too, you can do this before or after DE, you expect to see they cluster together. These are the controls, these are the experiments. If they don't cluster together, if some of them are going to the other side, means something is wrong, or there is no difference between your conditions, in that case. So you can prove that there is. But this is just to show how you can do these things. So this is, I'm just going to get the selected data and to another variable here with this data, role names, the res, this res selected was there before. I just get them and put it here into another easy to use data. Let me see what we have here. It should be something like this. Because in this res selected, as I showed you here, I have the results, but not the counts. But I need to use the counts now. How I get the counts? I get the role names, like from here, These are the row names using row names function. And the counts were in my data a variable. And if you put all the rows, you remember I put like some gene names here. But when I do this, basically I just put all the differentially expressed genes with this cutoffs into this variable, basically. So if I do this, and if I can look at the data, see, this is my data now. All these are differentially expressed genes using that cutoffs. So let me show the size of the data. See, I have like 1,200 data points, like 1,200 genes in these areas. So when you look at these blue areas on this plot, total are 1,200, like 1,205 total number. So what I want to do, I want to create first I want to cluster them to show this. That will show that this worked, and you can play with this. But again, like when I'm doing this, I need to normalize the values. Either after you find this values, you can normalize using AJAR's function, get on normalized matrix. This is a function that you can use, a method. This is a normalization method called like TMM. It's just trimming like up and it's just trimming the top and bottom quartiles, and it's just using the middle of the data after sorting, ordering all this data, and trying to adjust the medians in all data sets. This is that kind of method, but there are other methods like that. And like TPM, for example, another method that we already give you the table. You can open that table. You can open the table like we did here. You can use the TPM table and calculate your DE genes using row counts. But when you come to here, selection, you can use this thing to select, but use this TPM values here while you create your heat maps or other visualization. So this is another way we do. But in this case, I don't want to read that second file because this is easier. This is TMM, different normalization, because some people, like TPM, some people use TMM. There are different normalization techniques. And TPM, for example, is like transcript per million. So when you sum up all the values in TPM table, the total value will be 1,000,000. So then TPM value is good for comparing like different data sets, because you know that the total value is 1,000,000. And when you say like TPM1 in one data set and TPM1 in another data set, those are comparable because they are all normalized to 1,000,000 transcript per million. So these are different normalizations. These are still normalized, but it's not like adjusting everything to 1,000,000 in TMM. Still adjusting the medians that, when I'm showing the browser, I will show like what TMM is doing. I will show you like before normalization and after normalization. But here, basically, I'm just gonna normalize using TMM. Other methods here that you can look. There are other methods that, by the way, I wrote this function too. The real function name is this, calc norm factors, okay? If you, like I do like a couple of more things here, that's why I created that function to simplify. But if you want to see other normalization techniques here, methods, you can come here and look like TMM, TM, WSP. There are other things here that you can read. And there are some citations here too. Another one is RLE, for example. But all these normalizations are in the browser too. You can go and select from a box. Okay, so this is normalized now. It's ready to draw. So now what I'm going to do is, okay, so the other thing you need to do is you need to scale the data, because as you can see when in the log scale, some of them are like some values are so high And then when you create a heat map like this, if you don't scale them, one value is going to be like extremely high, and it will make it one like row red, the other rows will be like very pale, and you can actually change this center or scale later just to see how your heat map is going to be affected from that. But basically what I do is I just put this first to get the log, because without log, again, like one huge values, a couple small huge values are going to change everything. And if there are some zero in this normalized data, you cannot get the log of it, because log zero is infinite. So that's why we add a value like, a pseudo count 0.1, and it's going to this will be log 201 will be something, and it's not going to give an error. Otherwise, you can get an error, and this is not going to change anything. It's just going to put a value there. All zeros will be 0, 1, close to 0. So, and then what we do here is scale function. We are just using this LD, but to be able to scale only rows, you need to transpose the data using T. This is something specific here. Otherwise, if you don't transpose, you're gonna scale all column. So you don't want to do that. You want to scale using the rows. That's why we do this. And now I have like scaled entries now for everything. And now I'm ready to use a method, for example, Euclidean. There are different distance methods you can use while you do your clustering. This is a huge, another like, session to explain you this whole clustering methods and the distances. This is just going to look at every single gene in all samples and calculate root like square, like it's just going to use like root square of gene 1 in control sample 1 minus gene 1 in control replica 2. So that is like Euclidean distance, but you can use correlation values too to create the same thing. So this is, I did this with Euclidean here. The method is Euclidean. This is the dist function is going to create this. Basically, I'm just going to run this. And distances are going to be like this. Let me show the, it's going to be matrix. And you're going to have a value in between control replica 1 and 2 here, 3 and 2. So this is a symmetrical matrix. Distance function is just printing out only one side of this matrix, but you can actually have this distances from one to all the other samples. That's beautiful. Now it's ready to draw all this. This function. By the way, this is going to do that. It's not below. I don't know why it's here, but basically you're just going to run this plot function. And this hclust is doing hierarchical clustering. That's why you're seeing that hierarchy. And I just put a name with this main Euclidean. If you want to put another name for the x-axis, you can just write it here. And then when you plot, it is going to plot. See, these are those values that you see here. So distance from this sample to that sample is 20 something, 22. And the closest will be like replica 1 to 2. It's going to be the lowest number. See this 2, 22. This guy is 2. Control replica 1 and 2, the closest. And this is the largest distance in between these guys to these guys. That's why they are in different branches in this hierarchical tree. And then if you want to create your heat map, we have this heat map function. There are many more parameters here to change the colors, like, adding like the names on the x-axis or y-axis, like, and then change the orientation. But we all have this in the browser. But if you want to look at it here, first I get the transpose of this all values, because I want to use the scaled version. I'll show you a couple of things here, by the way, how it is looking. But and then when I create the heat map, Heat map means, by the way, here, this data, let me show how it is looking. After scaling and log, after you get the logs and scales, it's going to look like this. Same data, but scaled and log scaled a version of the same values per gene. So, and then you say that, like, you know, you want to have the rows, dendrogram will be in the columns. You want to have the column vectors, like these are true to visualize all the row and columns. And you can choose the colors. It's red, blue, or blue, red. There are many colors that you can define, many set of colors you can define. And we don't want to, row names, because when we put that here, they're going to be on top of each other. They're not going to look good unless your heat map is small, like you have a couple of genes. You can change, you can get a subset, and then draw only subset of genes you are looking for using this command. But you don't want to put the rows in that case, but we want to put the column names in its default. So I didn't say anything, but if you don't want, you just put like lab labels, role labels, whatever, NA. And the others are like not that important. Okay, I just put them to show it beautiful. So this is going to be your heat map. Hopefully these are going to be all selected up and down regulated genes. See, this is the heat map. So now you can play, for example, I don't want to do center or scale. Okay, so you're gonna see what I was talking about. They're not gonna look good. They're not gonna look like heat map. See, a couple of genes are red, and most of them are like, of course, over 0, but it's not scaled, as you can tell here. It's just log now, like the values you see in the scatter plot. These are those values now, just log scale, not scaled, not centered. But when you center and scale, what you do basically, you're distributing all of your data around 0. That's why the color key is going to be like around 0 after scaling. Let me scale them again. But just scaling is also not enough. You need to center. So let me do that first, just scaling. Did I do that? No, sorry. This, I forgot this line. So if you change anything, this affects this guy, this affects this, and this is here. So that's why you need to rerun them. See, something worked, like scaling worked, but they are not centered around 0. See, this is the scaling. It's like, you know, if you look at how to calculate z-scores, it's like a z-score calculations. Just scaling is for each value, it's finding the mean, and it's just that value minus mean divided by the standard deviation. It's like kind of z-score. So that's why it's coming around 0, but still not centered yet, because these values are count values, you know, raw count values. These are coming from there. That's why they are not like around 0 already. They are like positive values. That's why you need to bring them around 0. And now it's going to be like, it's going to look like how we want. See, this is the same function that we are using. The Euclidean function default here, like whatever we do here is here. So the clustering, so you don't need to do this cluster unless you need it, but you can just do this. One more thing I'm going to show you, the last thing is, if you want to, I usually use this, that's why, you know, that you can actually write your own clustering function here. And this function, I want to use my one minus correlation. And it usually is better in this type of data. Correlations are for, this is just for clustering, by the way, on top of it. The colors might be, everything will be the same. Or these lines, the values there are going to be the same, but the distance function will be correlation. and it works better. And when you can actually look at here too, like how we calculate this similarity using correlation and then convert it as distance and then plot it like this. But to be able to do the same thing in heat map function, we have to add these parameters, h class and dist function. You can change the distance functions for anything else. In the browser, we have like 10 different distance functions that you can try and see what's best for you. When I do this with the correlation, this is going to go down. Actually, see, and you see another way of showing the data. Okay, so I think we are done today. And any questions?
Alper, we have just one question from Kashi that he asks if how we can look for the gene names on the heat map for their exact locations.
See, that is kind of not easy to do that, like, because these are not interactive, you know.
Yeah.
That's why what I created is like the browser. That question is asked by many people, by the way, but in the browser, you know, in the future, like next session, I'm going to show you like shortly, but basically, maybe I can show you here very fast. But let me do this very fast. If you have time, by the way, if you don't have time, you can leave. I just want to show how easy in the browser. So basically what I do now, exactly the same thing I did on the other side with the browser. Here, you can upload
Could
your
you
own
share
file.
screen, please?
Yep.
I can see your screen.
You cannot again. Yeah. Okay, so basically I'm running the browser now, but I'm going to show you next week. So basically the same code is working in the background. Okay, all this code that you see in the bootcamp is here. It's running like the scatter plots. See, this is the same scatter plot. The good part of the browser is actually you can hover those genes, you know. You can hover these genes and see what they are. See, this is SCD1 and this is SCD1. So when you create a heat map, in that case, how you can create the heat map here was like you can press this NS, means like non-significant genes, it removed them. And when I select all these genes, it's going to create the same heat map that I created there. And this heat map is, and then when you, this is like, again, the same heat map. I use heat map 2 function, but then I create another heat map using another function, like heat map Lee, the name of that function. And you can convert this interactive heat map. And in that case, actually, you can hover and see the genes. And I'll show you one more thing. It takes more time because there are many genes. Maybe I could have done a smaller version of this, but it's going to be there in a sec. And maybe, I don't know why it's not coming fast. My computer is dead. I don't know. This is my old computer, that's why. Okay, so it's just taking more time now to draw here everything, but in your computer, most likely this is going to work faster. Oh my God, this is unresponsive. So let me do a smaller version of this. Yeah, my computer is dead. The memory is not enough now to cover this. Let me close my camera. It might work. Stop camera. Okay. I need to close things. GV. Exact. Yeah, don't open many things if your computer is not fast. Okay. Whatever. So I'm going to show this next time, but basically, when you hover this, what's it called? Heat map, you can actually see them here. Same thing like I did here. Okay. I don't want to take much of your time, but next Tuesday, I think I'm going to use my new computer. I can show this and you can, okay. Yeah, the reason is like, this is came, but took time. But let me do a small, see, I did this, but let me do a smaller version of this guy to play faster. So it's coming now. Okay, this is small. See, so you can do such things here. And I see gene names and stuff. The other thing you could do was, for example, if you want to see the gene that you are looking for, you can search those genes. Like, for example, maybe I could have done with FGF genes here on this search box. Let me do with FGF2 genes, or any gene list you can copy and paste here, and all FGF genes is going to be better. So then this was actually, I was trying to show you the selected gene are green here. And let me remove all the rest. See, all these selected genes, whatever I copied here, are going to be green on this plot. And when I select them, this box select, those are the heat map that you're looking for. And then when you hover, you can see everything here on this, or when you click on there too. So this is like what we wanted to do. Usually you discover your genes using these tools, but I'm going to show you, like, next Tuesday a little bit, like half an hour. Okay. Thank you very much for listening. Hopefully I'll talk to you guys later on Tuesday. Bye.
Thank you, Alpha.
Thanks. Bye.